Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's biweekly contest, design graph with shortest path calculator. The problem states that you are given a directed weighted graph consisting of n nodes and the edges of the graph are initially represented by the given array edges. So you are given an array edges which contains from I to I an edge of like the cost of the ith edge. So it says there's an edge starting from this node which goes to this node and it has a cost of this. Now you need to implement the graph class, and the graph class has three functions. First is the constructor, which initializes the object with n nodes and the given set of edges, right? Second is add edge. Basically, you're given a new edge and you just need to add it to the given graph. Then the third function is to find the shortest path between two given nodes, node 1 and node 2, right? And if there is no path, you have to return -1, right? So the problem is very straightforward. If you haven't solved this problem yet, I would strongly encourage you to pause the video right away and try to solve this problem by yourself. So let's look at what we have been given. So we have to implement this add edge function. So this add edge function could be just order one. You can just like whatever way you will represent the edge or the graph, you will just add the edge in that new graph. So it add edge function would be just order one function. Shortest path, again, you're given a graph is directed, and each weight is each the weight of each edge is different. So you have to apply Dijkstra here. uh, BFS would not work here because each of the weight here are different, right? So applying Dijkstra over a graph would take you order v plus e log v time, right? So here you can see v number of vertices are 100, number of edges are 100 square, right? So this would be 100 square into log of 100, right? And finally you have at most 100 calls. So this is currently uh, 10 to the power 4, right, into some small log factor, right? And this entire thing would be called 100 times. Like you will be applying the extra 100 times for two given nodes, right? So this entire complexity is 10 to the power 6 log of 100. So which will surely fit in the usual time constraint. So what we need to do, we need to just build the graph, and for whenever a shortest path function is called, just apply Dijkstra to figure out the distance between the two nodes, node 1 and node 2, right? So let's look at the code directly. uh, so the first thing is constructor. What we have done, we have saved the variable n, which is the number of nodes, and we are saving the graph as well. Now graph we are represented as an adjacency list. So each vertex, for each vertex we have a list of edges that vertex has, right? So for each edge, what I'm saying is from this node we have an edge to this node. So we will just add the edge which start from e of 0 and goes to e of 1, and we are also storing its cost in the second uh, part of the pair, right? Now once this graph is there, for add edge we will also do the same thing. We will just add one more edge that would be starting from edge of 0, right? Now finally shortest path, we will simply apply Dijkstra here. Initially we have initialized the distance of every node as 10 to the power 9. Now why 10 to the power 9? Because the maximum distance possible here is 10 to the power 8. There are 10 to the power 6 edges, right? Sorry, each edge can be of at most 10 to the power 6 cost. So and there are 100 nodes. So in the worst case, what can happen is you have to traverse all the 100 nodes one by one. So in the worst case, the weight or the final distance between two nodes can be 10 to the power 8. So we initialized with 10 to the power 9, which is greater than 10 to the power 8, right? And we initialized the distance of node 1 with 0 because we have to start with node 1. So distance between node 1 and node 1 is always 0, right? After that, this is standard extra. What we are doing, we are keeping a set of nodes. Again, you can use priority queue here as well. It depends on how you implement extra. But basically, we are putting in the distance and the node. And we are like this set is sorted by distance. So the node whose distance is minimum from the root would be at the top of this set. So that's what we are doing. We are popping the topmost element from the set, right? And then we are iterating over all its edges one by one. Now the edge will go to this particular node and will have a cost of this. So we are checking that what is the distance of that node currently. So if the minimum distance to that node is less than uh, basically if it is greater than the distance via this current node, then we will do something, otherwise we will continue, right? If latest known distance is already less, then we don't need to do anything. If latest known distance is actually greater than the distance between the current node and the distance to the target node, then we will simply erase the current node, update the distance of the target node, and finally insert the target node again to our set. So after this entire while loop ends, each vertex here would contain uh, the smallest distance starting from node 1. So we'll just check whether the distance is 10 to the power 9 or not. If it is 10 to the power 9, it means there is no path at all. So if there is no path, we have to return -1. Otherwise, there is some path which have some edge, which have some cost, and we just return that particular cost, right? So standard extra, if you are not like if you don't understand this entire part, I would encourage you to watch or read about the extra algorithm. You will be able to understand this pretty well. So with that, if you have any doubts in this problem, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.